Okay, 27 says, solve each inequality and graph the solution set. So this one's a little different, but can someone tell me what's one thing that's actually kind of nice about 27? Okay, so remember, you're making that number line, right? So you're making that number line, and you can already put 4 numbers on there. What are the 4 numbers you can put on there?
1,
2, and 4. You have 1, 2, and 4. And you remember from our last class, there were other types of numbers we needed. That's where it equals 0, where the equation is, if you made it equal, would make the equation true, right? There were other types of numbers we wanted to add in there if necessary, where we looked at the domain, like numbers that weren't in the domain. What's the domain of this function, though? Are there any numbers you can't plug in? No. So what's the domain of this? What's the domain? Yes. Come on. All real numbers. It's ARN. It's all real numbers. So are there any other numbers for us to put on this number line? No. No, there aren't. So how many regions do we need to test, Rachel? Here's one of them. 2, 3, and 4 of them. Exactly. So we need to pick a number in each of those regions. Can you get that? So what's a number to the left of 0 that's good to test? Left of 1. Sorry. How about 0, right? What about right here? How about, 1.5, 3 over 2? What about right here? 2.5, right? So that's what? Or 3. 3 is better, right? Yeah, 3 is better. And how about right here? 5. So you have to do each of these. You know that you say f of x is equal to x minus 1 times x minus 2 times x minus 4. And do you really care what the value is? Not really. You care if it's positive or negative, right? So let me just show you a shortcut. It's actually, this is what I like to do, because sometimes, could we keep on adding factors to that? Could I add like x plus 5 to the end of it? Just makes it harder or more involved to do this, right? So you could do the value, but you really only care where it's positive and where it's flat, Kelly, flat. So one thing you can actually do here, let me just show you what you can do. You can say the x value, x minus 1, x minus 2, x minus 4, and then the product. So what's the first x value? It was 0, right? So you do 0. What's 0 minus 1? Negative. 0 minus 2? Negative. Negative. And now you just multiply them all together, and what do you end up with? Negative, right? Do you care what the value is? No, you just do the sign. So what's the next value? 3 halves, right? 3 halves minus 1 is positive. Negative, and then what? 1.5 minus 4 is negative. What's a positive times a negative times a negative? Positive. And then what's the next one? 3 and 5 are the next two. Plug in 3. What do you get? Positive, positive, and negative. So what do you end up with? Negative. And then here you end up with positive, positive, and so it's what? So this question is asking, where is it less than 0? Right there, less than 0. So where is it going to be less than 0? Here and there, which are which regions? So we know it's negative, positive, negative, and. So how would you state the answer? Can someone tell me what the answer would be on this one? Calvin.
Less than 1.
X is what? Less than 1 or?
Between 2.
Correct. X is we want it to be greater than 2 and less than what? So it's one or the other. So it'd be one or the other right there.
I'm so glad you showed us that.
Do you see what I mean? Like that grid right there? And this grid really only comes up when you have more than 2. If it's only 2 things to multiply together, just think of it. But you're only interested as if it's positive or negative, right?
Yeah, I mean, I like that. I would use that.
Just remember, this is the one key to remember. This is less than 0, right? So you're positive or negative, correct? Are they always less than 0? No, you can make it less than 0 by subtracting whatever's over there. Just make sure you're checking the right inequality. Always make sure you're checking the right inequality you're not too happy with. I don't like that negative. What could you multiply everything by? You could just make, this is the same thing as x squared minus 3x. 3x minus 10 is equal to, because 0 times negative is still 0. Now, is that easier to factor? Yeah. You could, but it doesn't change the answer. Yeah, you absolutely could. That's actually a really, kind of like a mature thing to do for mathematics, because sometimes it can make a big difference later in mathematics. It is the same thing. Like, you could do that, and that negative could sit out there. It doesn't change the answer, though, so you can make it go to this line. What does this factor into, though? X plus what? 2. So therefore, x is equal to 5 or negative 2. Great. So the next one asks, though, so it's leading you through this. It gives you b. B is really similar. What does it say? Negative x squared plus 3x plus 10, like this, is greater than or equal to 0. Do we have the numbers to test? We have our boundaries. We have negative what? 2 and what? 5. So how many regions do we have? 1, 2, and 3 of them, right? So we need to test 3 numbers. What 3 numbers do you want to test? Well, right here, let's test 0, maybe 6, and what? -3. You have to go to the left of it, right? So if this right here, if that right there is f of x, we need to do f of -3, right? It's going to be -3 squared plus 3 times -3 plus 10, like this. So what's -3 squared? Oh, come on. What is it? -9 minus 9 plus 10. Is that going to be positive or negative? That's less than 0, right? Or we can just say, let's just say what the number is. What is it? It's going to be negative what? Tell me what it is. -8, yeah. So then you have to do f of what? 0? Well, that's going to be what? What's f of 0 going to be? 10. Thank you, Alyssa. And then f of what? 6? Is this kind of big? -6 squared plus 3 times 6 plus what? 10? -36 plus 18 plus 10, so it's plus 20, so it's -8. So it goes what? Negative, positive, or? Now be very careful. Can someone tell me what the answer to this is based on that? Be very careful. What's the answer? This question is asking where it's greater than or equal to. So can you tell me what the answer to this is? X what?
X is greater than
Equal to what? -2 and less than or equal to 5. Because you see they're equal to 0 here. And you want that because of what? This thing. It's greater than or equal to, right? So do you see the difference here? It includes the equal signs. So here's your answer right there. Be very careful.
So if there's in the
How many regions are we going to have on this one? Nope. 4 of them. So, you know, for this one, you know, it's going to be x is equal to -2, right? X is equal to 3/4, and x is equal to -7/2. So there are 4 different numbers. There's -7/2, there's -2, and there's what? 3/4. So how many regions are there? 1, 2, 3, and 4 of them. There they are. That's where they equal 0. So again, you just need to test the sign. So let's pick the numbers we're going to use. What's to the left of -2.5? How about -3?
like 7.5.
Yeah, -7/2 is negative. Oh, -7. Sorry, -7/2 is -3.5. You're absolutely right. It's -4. So what about here? Negative what? 3. How about 0? And how about 1? So again, remember that thing I showed you? You have x, and what are the 3 things? X plus 2. What was it? 4x minus 3?
Yes, and 2x plus 7.
2x plus 7, and then the product, right? So the first one was what? So the values are -4, -3, 0, and what? 1. So let's plug in -4. You get negative, definitely negative, negative, because it's -8 plus 7 is -1. So what's the product? Plug in -3, you get negative, negative, positive. So what's this come out to be? Positive. 0 is going to be positive, negative, positive. So what's that going to be? Negative. And plug in 1 in, what do you get? Positive, 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 and now you get accustomed. Do you see this alternating negative, positive, negative, positive? Is it always going to be like that? No, it could go negative, 0, negative. You could have 2 negatives in a row. It's not guaranteed to alternate. It is not. How do you know what?
How do you know what the product is?
Because like for example, a negative times a negative times a negative is a negative. So you just do the products across. What is the product of those? So you don't care what the value is. You just want positive or negative. So only do the positive or negative. So what did we say it goes? It goes negative, positive, negative, positive. Can someone therefore tell me what's the answer to this one? Very carefully. What's the answer? We want it greater than or equal to 0. So what is it going to be? Greater than or equal to what? There's 2 places, right? Yeah, -7/2 all the way up to what? Nope. -2. Look, it's right there. To -2. Look at that region right there. Look at the purple region. It's positive from -2, 7/2, and it's equal to 0 there, all the way up to -2. But then there's another one. What is it? I'm not asking anything that's not right there in front of you guys. Where is it? So it's x greater than what? X greater than or equal to 3/4. So this would be your answer right here. That would be your answer right there. Does that make sense? What's the question, Kelly? And it's greater than or equal to -7/2. What about this region right there? That's just x is greater than or equal to 3/4. Exactly. Now, in calculus, you get to do really cool things like, remember, we looked at vertices. Why did we look at the vertexes of parabolas? Because we're looking for the...
Lowest height.
Exactly. Now, can you ask the same question on these? Sure. How many vertices do you see? Well, I see 1 and 2, right? Those are highest and lowest points. Are those interesting points to find if this modeled like a real-life behavior? Sure. But here's the thing. Parabolas are symmetric, right? We really like that symmetry thing, that -b/2a, that gives us -b/2a. Is symmetry guaranteed on cubics? No. So, for example, this curve right here, is this curve symmetric over this like axis right here? Like this, imagine, no, it's not. You need calculus to find that point. You need calculus to find that point. It's one of the first things you learn in calculus, actually, is how to find those points. What's really cool is the way you find them in calculus. If you are on a roller, could this be a roller coaster? Sure, right? You could be on a roller coaster like this. If you're on a roller coaster and you get to the top here, what's that? What do you feel at that top point when you're on a roller coaster?
Oh, your stomach drops.
Your stomach drops a little bit, right? Because you're not going up and you're not going down. At this point, so if you're traveling up, 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 and then at this point, what do you start doing? Start traveling down. The rate of change upwards is 0 right here. Calculus is 2 things. The calculus you see in high school is 2 things: the study of rates of change and the areas and volumes of things. That's really what all of calculus is.
It sounds really simple, but it's totally not.
It totally is way simpler than people make it out to be. Way simpler than people make it out to be. They look at it and they're like, I don't know what that letter means, so I just don't think it's crazy. It's not bad. Area under the curve. That statement right there means find the area under the curve. This is what that means. This is the integral from 1 to 2 of that function. And what you do when you learn how to do that is find that area. It's kind of cool, because is that a straight line right there? No, it's not. So you can't pretend like it's a straight line. You can get an estimate with a straight line, but if you want the exact area, you can use calculus. This is integral calculus to find the area of that thing.
When would that be
In real life.
In real life,
Yeah.
just about everything that you have in life that models anything is not a straight line. Nothing, just about nothing is a straight line, right? I'm explaining the story. If you want me to explain it, let me get the sentence out. Nothing you deal with in real life is a straight line, pretty much. For example, the velocity of a car over time, right? Guess what the area under the curve of the velocity function is? The distance traveled. So basically, if you know the velocity of a car over time, guess what you can find? The distance it traveled using this exact math.
Oh my god, it's so cool.
Everything you see in this room, like literally everything, was manufactured by people who had to be very exact about process and manufacture, right? You had to know, like, see this board right here? It's cut at a certain angle, right? They had to figure out, like, this is probably poured. This is probably like some fiberglass kind of deal, right? So they had to know, if I'm going to make 1,000,000 of these, exactly, like literally exactly how much of this stuff do I need, right? So what do they have? They have a function that models the edge of this curve right here, a function that models this indent, and they can calculate the volume exactly and then multiply by 1,000,000, and that's how much of that stuff they need.
So cool.
Like literally everything you look at in here is modeled by a function. Like anything that is made or like processed uses some sort of function that is almost certainly not a straight line.
Yeah.
Like literally, there's nature likes to sometimes model straight lines. Like for example, how many people have taken biology?
Oh.
Have you ever seen a curve that looks like this before? Ready? I'm going to give you a graph. You might have seen this before. Have you ever seen a graph that looks like this before?
Yes.
And sometimes you see it. Sometimes you'll see like a field. It'll look like this. It'll go up and it'll come down. You know, or you'll see something like this. It'll come up. What is this? Anybody know what that is? You're really interested in this line right here. Anybody know what that is? It's called the carrying capacity of a population. These are logistic curves, right? A given environment has a carrying capacity, a maximum amount of a population that can be supported. So what happens? Well, the population starts growing, right? And then it usually goes a little bit above, right? But then the environment can't support it, so they start dying off, but then they go a little bit below, and then they go a little bit up. So there's this carrying capacity, right? Because of, yeah, so the idea is there are specific functions that model this, right? So what do? This is time and this is population, right? So you can put points on here. Do the points exactly match up with this thing? No, they don't exactly match up with it. It's a trend line. It's like not. It's a trend function, right? You say trend line, right? But the thing is, lines imply like linearity. Yeah. These aren't linear. Point being, nature, life, reality never really follows an exact model, but can you model it really closely? Yeah. Like, what is nature trying to do? And it really does follow these certain curves that we've defined as such. Yeah. So anyway, the point is, where do you use calculus? All over the place. Like, if you're going to be just like literally, quite literally, almost, I would say any scientific field, if you wanted to major in anything related to the science field or in science, you have to get through calculus because it's like the core math that you at least have to get through. That's like the foundation for a ton of what you do in any of those other sciences. Anyway, to answer your question, that's why. That's good. I like that. That's cool. Anyway, okay, put everything away except a pencil. There you go.
Or death hour. Or death time.
I was literally watching my friend do her homework and I was just like, what? It was horrible. She was just like sitting. She was like 300 calculus. She was sitting there on it and like, I'm like, how? Like she's never gotten below like 97.
What?
Great.
Yeah. What?
Did you hear about the bombing?
Yeah.
That's a city where
Where you from?
that's a city where I live.
Where you live? Okay, you can start this once you get it. You get 3 minutes. There's no trick to it. It's not meant to be super hard. It's a straightforward question. When you're done, flip it over and draw me a pretty picture.
Mr. Seamon, there were so many our golden retrievers on campus today.
Really?
Or not today, like this past weekend. They were just everywhere. I was like, what is going on?
Golden retrievers on campus. Okay, go for it, kids.